Okay. So, Dave, now they have discussion. Do you want to introduce discussion time? Say something. We have about 1 hour. And yeah. So we have basically two topics to discuss. So in the morning we have discussion about the megathrusts and tsunami. And then we have subduction and mantle convection. I think first I want to let Dave speak.
Well, I think that we should throw the floor at the first topic about the tsunami. I think the question raised by Sergei about whether or not the landslide contribute significantly to generation of tsunami waves. It's a very interesting point. So I would like to see some discussion on this. Stefan, do you have anything else to add?
Well, it's a very broad topic. I mean, I would have a lot to add, but
Like I think that only this year with the Tohoku earthquake,
Tohoku is still, it's still a sort of an open topic. There are very few confirmed landslide tsunamis. For instance, on the east coast of the U.S., there is a 1929 Grand Bang.
I don't think the mic's
No, I don't think it's working.
That's why it's not exactly the US.
No, exactly. Of course.
It wasn't Canada.
It's Canada. I meant on the east coast of the North American continent. So 1929, but 1929 there was a moderate earthquake, 7.2, which is still the largest observed on the Atlantic coast, of the upper east coast, that triggered an underwater landslide. It's not worth. That landslide caused a tsunami that I out of memory kept 29 people in Newfoundland. So that's one case where a moderate earthquake triggered a fairly large underwater landslide that triggered a tsunami. There is also the 1998 Papua New Guinea case. Neil, knows a lot about it, and I contributed to some of the modeling where, based on the cruises and the geology, that was another case with a moderate earthquake, 7.2 also roughly, that may have created a moderate tsunami that didn't do a lot of damage, but then with a delay there was a fairly large seabed rotational failure that caused a major tsunami, perhaps responsible for 2,000 deaths, and much larger run-ups up to 60 meters. So that was kind of an eye-opener for the community of tsunami modelers who had not really considered underwater landslides as a major risk. And so since then, say in 2004, when there was those extremely large run-ups in Banda Aceh in northern Sumatra, people started looking for additional seabed failures. Nothing that I know of has been found as of yet, but as far as I know, no model using the seismic source in Sumatra has been able to explain. I think the maximum run-up measured there was 39 meters in one of the narrow valleys. And so again, in Tohoku, we're facing the same situation where the best modeling we can do of the seismic source does not explain all the observations. So we've got to be looking for something else. But there are a number of processes, as was mentioned, the splay faults, the submarine mass failures, the combination of both. Until we had direct observation, that happened in Papua New Guinea. It's when finally there were marine geology cruises, multi-beam surveys, coring, I believe, as well. In Papua New Guinea. But at least
exactly sure.
underwater vehicles went down and they looked at yeah. So you need a lot of corroborating evidence. Now here we have evidence through modeling and we're trying to gather evidence. So I think the lesson here is that we need to keep an open mind and for future large events we should consider that perhaps there could be other processes that could contribute to runoff. It's very important for other subduction zones. So.
If I may add a few words to what Stefan summarized very well. I think when we try to oppose a landslide and an earthquake, it is because we try to oppose two different physical processes. And if there are different physical processes, it means that somehow there are characteristics which are inherently different. And those characteristics are what we would refer to probably as invariants otherwise. Take an earthquake, there could be big earthquakes and small earthquakes, but there's something common to it that means that we call it an earthquake, a dislocation source. That's the invariant. And these invariants are these kinds of things that I try to mention in my talk, aspect ratios of this divided by that, strain release, which is essentially slip over size, and things like this. So, based on these invariants, some of the work Kostas Sinlakis and I did at some point was to theoretically explain what we refer to as the Blafker rule. Because when we were in Unimark with George Blafker in 2001, he sort of jokingly told us, well, if you have so much slip on fault, you're going to have so much run. And that caught our mind, and we sort of proved later that there was some theoretical rationale behind it. So I would perhaps take a slight exception to what you said, Stefan, that in the case of Sumatra, those 39 meters of runout, part of it is perhaps also in the form of a splash on it. But let's take the 39 meters at face value, divide it by 2, and you will find the slip that you need on the fault. And that's 20 meters. Magnitude 9.3, yeah, sure, we can have 20 meters. So, in a sense, that means that ballpark figure, order of magnitude, back of the envelope calculation, we don't need the landslide. Now, if you move 1,200 kilometers of fault line, 20 meters in some areas, you're bound to have a landslide somewhere. You're bound to shake loose something which is precarious. And so, there must have been some landslides, and if you look for them, you find them. Now, did they contribute to the big picture? Were they responsible for tens of thousands of deaths in Sri Lanka and India and 300 in Somalia? The answer is most probably no, because we can model Somalia from the 9 meters of runout in Somalia, which killed 300 people at the other end of the Indian Ocean. We can model it without the landslide. So in those cases where we are really faced with something clearly unexplainable, we have two avenues. Either we say the earthquake violated the scaling nodes, and this is what the models of Thornley and others do. They say, hey, I put 50 meters of slip there over a little patch which is 50 kilometers across, and that basically is a humongous strain range which violate everything which has been written about the seismic source before. Perhaps, yes, we should do it, perhaps. Or, as you do, you say, well, I'm going to involve a landslide. And so, I was very intrigued by your talk this morning because, as much as I understand the reservation which must go with proposing the landslide before we find it, it would obviate another problem. It would get rid of another problem, which would be these bilateral scaling laws. Another thing which I want to say about landslides is that in the cases such as Papua New Guinea, in which I was somewhat involved, we were lucky because of the delay. This is the delay which cracked the case. The fact that the whatever caused the tsunami took place about 12 minutes, if I remember well, 13 minutes after the earthquake. So it couldn't be the earthquake because there were things out there. There were testimonies. There were all kinds of evidence which showed that it couldn't be co-seismic. It couldn't be at the same time as the earthquake. And this was repeated. For example, we think that in the Makran off the coast of Pakistan in 1945, it's the same story. The tsunami is late to the extent that it got a distinguished oceanographer in the Seychelles to have a paper in Nature where he shows that the ocean is on the average 1,000 meters deep. Because he used the arrival time of the tsunami to infer the depth of the ocean, assuming that it started at the origin time of the earthquake. And we've known now, and that's a proof actually, that there was an ancillary phenomenon. Now, another thing which is, I think, a clue, and I wonder if we could look into this in the case of Tohoku, but if it hasn't been done yet, is the fact that a landslide, and there was a phenomenal paper by Tony Darwin, which I was privileged to review in 1993. It was quite a burden, but a landslide fundamentally differs from an earthquake in what happens at the end. In an earthquake fault, the ends of the fault are still continuous. You can drive around the tip of an earthquake. You cannot drive around the tip of a landslide because you have a physical separation there. And what it means is that once you've effected that physical separation, once you've cut the piece which is going to slide, you can move it a distance which is much, much greater than its size. Okay? And you can entrain something on the ocean floor to enormous distances to the extent that you break it. And I'm talking about cables. I'm talking about telegraphic cables. Every time there was an earthquake at sea which broke a telegraphic cable or a telephone cable, a fiber optics cable these days, every time they went back to fix it, and they actually looked at what was there, what was broken, they found turbidity currents. They found a big seafloor mass movement. And so we've come to, perhaps too confidently, but we've come to associate these breaks of telegraphic cable, of which the most famous one is probably 1929 Newfoundland. We've come to associate them as proxies to landslides. Because every time they've been fixed, they found the landslide. So that may be another way to look for landslides. Now, I've spoken too much, I think, this one, so I'll pass the mic to someone else.
Just want to just give you a general question. As the physical process of generation of the tsunamis can be conceptually different between earthquake and landslide, it's going to be maybe interesting to theoretically arrive to make a discrimination and the observation between these two phenomena, and do you think that it's maybe possible, to make this discrimination and try to separate the effect, the contribution of the two parts?
I think that the process, I would say,
the process is inherently the same, which is that you move something which is solid, although by the time the landslide evolves, it can develop into a kind of slurry, and we could argue what is solid and what becomes a viscous fluid and so on. But initially, you move something which is solid, you displace it in the water, so you've got to move the water around and so on. and this is the disturbance, initial disturbance, which is the now, of course, because the phenomena are different, things such as these dimensionless invariants, which are different, and perhaps also the things which possess a dimension, like velocities, but actually this is referred to the velocity of propagation of a tsunami. So in the end, it is a dimensionless parameter. Because these parameters are different in the two cases, then you have different properties of the tsunamis, like wavelengths and all that. But inherently, and correct me if I'm wrong, I think inherently it's just a simple story that you're moving something inside the mass of water and disturbing the water.
I agree with Emil. I would just add, from the point of view of a wave modeler, that the scales are typically different. We've seen in Tohoku, say, the scale of the subduction area that ruptured was about 500 by 200 kilometers. Now, what we locate as far as a landslide is about 10 times smaller than that, all right, in each dimension, so 100 times in area. So the waves you're making are a lot smaller. Now, the physics of smaller waves is different in the sense that they have frequency dispersion. Now, frequency dispersion leads to trains. So, for instance, in our simulation, well, in the Daoguri closest to Japan, there is clearly a first large peak, which is a non-dispersive part, mostly generated by the main earthquake. And then you have a series of smaller oscillations, indicating that some dispersive processes took place. You see that also to some extent in the GPS buoys. And that is a sign, first of all, that smaller scale seabed processes, I'm not going to say landslides, but took place. The second thing is the focusing on shore, which is much more intense usually for landslides. You see that in modeling, in experiments. So you get that beam of energy, and the far field effect, as Emil was pointing out earlier, is much less, because those far field effects dissipate much quicker. Yes. Right. Right. So
when you are close to the coast or the harbor and tsunami also maybe difference, that is probably
right.
Local effect also would be affected.
So there are telltales in the signals you observe. So in this case, the third thing in Tohoku, because well, if you do a direct inversion of the tsunami signals like Facility Tofted or others, so you can actually create a source that corresponds to the observed waves. So you see where on the seabed you should have displacement. And so you see in the case of Tohoku that you should have displacement further north outside of the zone of the seismic rupture, where it doesn't show up in the seismic inversion, it doesn't show up in the GPS data inferred from the earthquake. So there's something else that took place there that is needed to observe, to explain the observation. So as Emil was saying...
This is also maybe because we have mainly the observation just on one side.
No, we have observations all along on the shore. We have pressure sensors on the seafloor that I didn't show. And they all indicate that to obtain those waves north of the rupture, there was need to have, and the travel time that I showed, there was need to have some other failures there that don't seem to be related to the microseismic event. So, whereas this is a landslide, a rotational slide, a slave fold. You observe it in the atmospheric data. So, this is a series of evidence that points towards looking for something there. And all we did is explain it with, rotational seabed mechanism. And when you do that in the modeling, it matches the observations quite well. That's all I can say at the moment, until we have direct observations. Any other questions?
I have a question to Professor Geller. You showed the hazard map of Japan, and I looked and there was no hazard south of, to the west of Kyushu. Is there
is there a possibility that a big earthquake can also occur west of Kyushu? If that's the case, I think tsunami or big earthquake, I mean, if there is a tsunami that could affect Korea, but if it happens in the middle part of Japan, Japan island basically blocks. So I was wondering, what are the possibilities? Yeah.
Well, first of all, as to the hazard map itself, is made by a committee of the Japanese government. So I'm not responsible for their map, and as you know, of course, I've been quite critical. Now, as to your question, the map that you correctly stated, the map doesn't really suggest any big hazard in the Sea of Japan. But if we look at prehistoric, pre-instrumental seismology, it's very well known there was a large earthquake in the year 1026 in the Sea of Japan. And it caused a big tsunami in what's now called Shimane Prefecture in Japan.
How about the Ryukyu Trench, around the Ryukyu Trench?
Well, I don't know. I don't know that I'm going to ask Emil about this in a second. But one of the big questions is, as you know, and I think everyone knows, right now the Ryukyu Trench, if you go back to the Ralph and Kanamori paper, for example, was thought not to be capable of being able to have big earthquakes. And I don't know what the pre-instrumental history of the Ryukyus is. I suspect that it has some potential, but I'd like to ask Emil to answer.
Well, I find myself in the unexpected situation of coming to the help of Yellow-san but I think regarding Japanese seismicity, but I think there is a 1771 major tsunami in the Ryukyus. Correct me if I'm wrong, but we don't know if it involves a big landslide, maybe, or if it involves a major earthquake. Now, there may be some hope for Korea because let's assume from Ryukyu. I mean, if it was in the Ryukyu trench, because the tsunami, if it's in the trench area, it's going to be generated in relatively deep water, and then when you generate a tsunami in deep water, and then you transition it on a very long, and I'm mentioning very long body of shallow water, it loses some of its energy. And this is what happened in parts of the Bay of Bengal during Sumatra. India was affected pretty bad, but to the north, Burma and Bangladesh were not. And this is probably, we explain it by the fact that the tsunami sort of faltered after it went in these extremely shallow waters. And it lost its energy interacting with the bottom, and it was dispersed and so on. And so perhaps then there is some hope that if there was a catastrophic earthquake in the Ryukyus, by the time it reaches Korea and China, let me be very careful, the Western Sea, right? It would, yes, Yellow Sea. But I thought Korea refers to as Western Sea.
Yeah, Korea we said Western.
Yes. So I wanted to be politically correct and call it the Western Sea here. But by the time it reaches, it's going to waste a lot of momentum and energy. That's my best hope. Now, as to your question, the western side of Kyushu is a passive margin, is it not? The western side of Kyushu, or is it? Maybe I'm wrong.
In 2005.
Yes.
Magnitude 7.0 occurred in the western Kyushu.
Okay.
So it's certainly seismogenic. both beneath nuclear arc and also in the background.
Okay. But what was the mechanism? Crossfall?
Thrust fault. But it's a cross earthquake.
Okay.
Magnitude 7.0. Close to South Korea. Close to Jeju.
Okay.
Yeah, so I want to make one suggestion. This is outside my field, but in the past 20 years or 30 years, there's been fantastic progress in paleo tsunami research. And we don't really know what the risk on the Sea of Japan is. So it would be very good for scientists from Korea and South Korea, North Korea, and China, and Russia, and also Japan to all get together and make some cooperative project to look for paleo tsunami evidence. That, like in the case of Tohoku, Japan, you can't just go anywhere and find the paleo tsunamis. You need some flat place where the deposits accumulate. Like, for example, the Sentai Basin is ideal. So, the history of this actually started in 1983. After the Sea of Japan earthquake off Akita Prefecture in Japan, then Japanese geologists went and they could see the very fresh turbidite-type tsunami deposits, and then that gave them some idea of what to look for. And then they found them in Tohoku on the other side. So I think it would be a very good idea for the scientists from all of those countries to get together and do a cooperative project. That's the only way to really find the answer.
I think that's a very good suggestion. I just wanted to offer just a word of caution. The turbidites in depths are clear indicators usually of tsunamis, but the deposits on shore, when you can core them, are of course also important, especially in the dating and so forth. The problem often, particularly, say, if you take the east coast of the United States in the hurricanes, they erase. I mean, we can't find any paleo tsunami evidence on the east coast. There was, of course, a glacier that covered north of New York, but even to the south, there should be evidence, but because there were so many storms, it's hard to find the difference. Now, I don't know about the typhoons. That's what I was going to ask in Japan, how they affect in the Yellow Sea, perhaps whatever may have been deposited by Korean tsunamis.
I don't know.
One key point is marine, shell fossils, not fossils, but all the kind of shell fossils is marine origin. And abnormally huge tsunami can be detected without noise. If we find such sediments plus marine living fossils. So but there's a smaller scale one, could be erased by typhoon. So they are difficult. So this is the point. And we...
Okay. You finished? Okay. I quite agree with Professor Keller, and I think the eastern margin of Japan Sea is very seismic. And as Professor Keller mentioned, in 1983, a big earthquake with magnitude 7.8 occurred. And also 10 years later, in 1993, off Hokkaido, the magnitude was 7.8, and about 100 people were killed by this time. Okay. Anyway, the eastern margin of Japan Sea is very seismic. We certainly should pay attention to that. And also tomorrow I will show you a cooperation with Korean scientists. Recently we have done a cooperation with Korean scientists in Jiga. We processed the data from both South Korea and West Japan, and we got new result about the structure in this field. I will show tomorrow. Thank you. So the international cooperation in East Asia is very, very important and necessary.
No, I don't.
Ideas? For example, about geodynamics. We saw today a lot of talks about free surface in a geodynamic model of subduction. wonder if modelers have something to say about it in geodynamics, because we model when we model subduction, usually we sort of cheat a little bit, put instead of a real free surface, what we call a sticky layer, because this helps to reproduce many features of geodynamic systems. So, for example, plate tectonics, it looks more realistic, or trench retreat or advanced. But in this way, we also miss some, say, the opportunity to model more high resolution, the coupling with the surface process, where you have the generation of the fault and the truss fault. So maybe somebody has some comments about how we could model the real free surface and the real brittle. Scott, did you say something?
Elastic forces into play.
Sorry?
You need to take elastic forces into play.
Yeah.
To do it.
So we need model about, so basically implement already plasticity and elasticity. For example, we have the model of Taras, Taras scalar that is modeling explicitly the forces, but free surface is difficult. Or we have this model that we use finite element, like abacus, where you have basically. What I'm saying is that there is a gap to fill between say the large scale of geodynamics and the mesoscale subduction scale, in order to couple with the truss fault and the possibility to model it. Yeah? Scott.
Well, there's a community of people who are not particularly well represented at this meeting, but we may hear a little bit from some tomorrow who actually look at much smaller scale geodynamic models. And, you know, there are a lot more observations that, you know, when you're trying to look at global plate scales that are very difficult to, you know, resolve. But I mean, there's, you know, people who look at the mantle wedge who, you know, you bring a lot more constraints into the modeling, and there are, you know, seismologists who look at the coupling between the overriding and the subducting plate and have a lot more constraints than can be put into these sorts of global models. But I mean, and that's where I would see there being a much greater potential. I think it's interesting that we tried to bring different communities together that normally do not listen to each other's talks and so forth. And I've been listening to the talks this morning and the talks this afternoon. It was very difficult for me to see that there is much common ground, at least at this point, between the two types of things. It's almost like they're talking about two entirely different processes that you're talking about, even though you're looking at subduction zones.
Maybe the small scale subduction zone analysis is the link between the discussion of this morning.
Yeah, but I think there is a scale that we may see some of it tomorrow, where I think there's a possibility. But the other thing I would say is that there were a lot of talks today talking about a free surface and people trying to implement this. And it's sort of interesting, but it seems to me that it's time, if a free surface is really important, there are mathematically correct ways to implement it. And doing things like sticky air and other things that are easy, but mathematically I'm not entirely sure what they mean. You know, maybe it's time to actually implement a real free surface if it's important to do free surface, rather than do a lot of scaling analysis on some sort of method that's easy to implement.
I just want to
to make a comment that I would agree with Scott. There's probably a gap between the scale of the dynamics models and the topic we've been talking about this morning. But the point that I would like to make is that essentially it's the whole system works all together. So it's a kind of a multi-scale approach to it. So the message that, or at least the interface between the geodynamics models and what we see this morning is essentially how you couple the two. So it's not really, in my opinion, it's not really the discussion of the free surface or the mantle flow itself or how you can interpret the subduction, but it's the dynamics. So essentially, how do you convert the stresses from the subduction to stresses that accumulate and then release at the subduction zones. So probably rather than talking about the implementation of these surfaces, we should really talk about the characteristic landscapes which you get from the observation from the mountain. So I don't really believe that it's relevant to talk about here about the global pattern, but probably something a little more regional. So when we have a look at something at for instance, at the scale of South America, having a look at that, and you can really start to observe properly, better, with the coupling with the upper plate, some stress patterns that have some gradients that you will never see in the global models, but still they match beautifully the geological evolution. So you observe the shield, or at least the stress that propagates along and localizes into plates, the thickening of the Andes, the deformation of geological time. So eventually, in that region, you end up with a model that matches the evolution of the last X million years. It's fully dynamics, so represents a present-day configuration of the stresses that is valid, geologically valid. Then you can use that as an input for the short-term evolution. So rather than having climatic boundary conditions that are not constrained, or assumption on which are the rates measured by GPS or whatever, you can build with these geodynamic models something that is self-consistent over geological scales and reproduce the precise present-day configuration of stresses. That's, I would say, in my opinion, it's a starting point. So, of course, you want to model the fold, the interaction of the seismogenic cycle, but if you can start from the larger picture, you can scale up. And in my opinion, the larger picture is the regional subduction evolution, so rather than the global. So it's probably something we should talk about rather than other technicalities.
Yes, I agree. I mean, it's the regional scale is sort of the largest scale because the force that gets released during the megathrusts is the one that's subduction zone. We know it is the slab pool of the slab. So that's basically where the forces come from. And also the length scale of the larger megathrust is about, let's say, 1,000 kilometers squared. So it's also more or less a scale kind of a regional. Say something?
Thank you. So I want to bounce some comments to Scott. So I was also surprised to witness more connections between earthquake studies and slab dynamics on the larger scale. And I think there are some very obvious interactions between them. For example, I've seen several strength models with current relay agents and other curiosities of the culinary taste. But the Tohoku earthquake was actually an example where you can imagine that there was a complete stress rock. So complete release of the stress in the lithosphere. So that I think that goes against this traditional modeling of the strength of the lithosphere, at least in the upper segment. So that's one direction of coupling where the earthquake cycle actually affects the stress evolution at the largest scale. Potentially, I don't know the answer, but that's something that can be investigated. On the other side, other direction of coupling, obviously, the large-scale dynamic models of lithosphere evolution can provide other studies that look at smallest features, some background information on mechanical properties, initial stress. So a big problem for earthquake modeling is to come out with a spatial distribution of pre-stress for that is going to initiate the modeling. And also for other studies such as studies of post-seismic transients that provide a way to constrain the viscosity of the lithosphere at the regional scale, should find a way to connect with the geodynamical studies. So I don't know where this community is going, but that's something I would like to see.
Yeah, I mean, in general, there have been many works that have shown that basically, if you don't model subduction in a purely dynamic way, you just impose some kinematic conditions, then what happens is that you get always something energetically, some failure, so put energy in the system or get out, and it's not settling system, then you get some erroneous result.
You could go back to Jeff Davies in 1989. I mean, he showed, something that so-called self-consistent models are not doing,
yes.
Which is that if you put an initial condition in that has way more buoyancy than the model can sustain, you set up an initial condition that could never have been obtained by the model that you started with. So, I mean, you need to at least do that correctly. And that's not being done in many models that one has seen.
Yeah, I agree.
So the term self-consistent can be a little self-congratulatory. We produce self-consistent models. In one sense, self-consistent.
Just mean, if the boundary conditions that are not physically consistent, they want to introduce energy or something to the system. You observe it today, you put the system, you get diffusion, and then diffusion increases when it becomes elastic. So eventually we'll do it. So I think when we go toward the surface, we want to model something that people observe, so we see even more than it gets far away from nature. That's why it's important. Say something?
Yeah, I'd like to add a comment on the idea of the propagation stresses regarding what Emil Calvary showed. In fact, essentially, the Raffen-Kanamori, yes, Emil, I'm talking about you. The Raffen-Kanamori prediction was, of course, refuted in the last years. But one of the messages we get from the now distribution, which seems to be flat, so the same magnitude, is completely independent of the age of the subducting plate, or maybe the convergence velocity itself. So it also tells you something that it doesn't matter the property of the single point, so the 2D approximation or the punctual measuration in one place. You always have the same stress level everywhere. So if the seismic release indicates that the amount of stress that you've been able to accumulate. So probably the point is not a 2D model anymore. So you cannot measure in a place the velocity of convergence perpendicular to the trench or the age of the point. It's likely a propagation of stress that is from everywhere else. So eventually you have an homogenization of stress. And so from the dynamic model, what we learned is that there is a length, characteristic length, that you can propagate the stresses across, is this invariant we're talking about, but not more than that. So that's why you measure some earthquakes, the seismic release somewhere in Chile, but you cannot really tell that the stress comes from the dynamics of that 2D model. So probably it's coming from stresses that might be larger, where somewhere else the pool, the slab pool is larger and propagates laterally. So, and this is an invariant because, as you showed, eventually the rigidity of the plates is the same everywhere. So eventually you release a stress somewhere that comes from somewhere else. So probably that's what the dynamic models will have.
Yes, possibly. Yes, no, I agree with what you said. I think my friend Geller wants to answer was believing that he would back.
Oh, well, I just want to add one point to what you said, which is that some of the recent work by Jan Cohen from UCLA, both by himself and in collaboration with David Jackson, has done statistics on the maximum magnitude from all of the subduction zones. And if we strictly report his results, he hasn't shown that the maximum magnitude is the same everywhere. But what he's shown is that within the present statistical uncertainty, you cannot say statistically significantly that it's different. It may be different, but we don't have the grounds as yet for saying so.
I want to add one thing, and I'm sorry I was a little bit less than attentive when you started your question, because I was writing to Dabenja to tell him that the 2005 earthquake is actually much smaller than he thinks. The seismic moment is less than 10 to the 26, and it's a strike-slip earthquake. I just pulled it from the CMT global data set. So what it tells us is it's probably one of these snappy earthquakes where the magnitude from GMA is very high because it's some kind of acceleration magnitude, intensity magnitude of some kind, but the seismic moment is not so big. So going back to Professor Lee, I would say that probably that would quiet down the kind of hazard towards Korea, because it's probably some kind of minor little crustal fault like we had in Seattle in 2001, for example.
Similar one may occur close to Korea.
Ah, yes. But at this level, they're not going to cause any tsunamis.
It may cause some local hazard.
Yeah, no, I agree, but it's not going to export tsunami hazard to Korea. Okay, thank you.
Sorry, I'm not getting controversial here. I disagree with what Fabio said about the homogenization of stress and how you can interpret the failure of the Canamorian rough prediction. In fact, I think it's quite the opposite. The failure of these predictions is because the stress is very heterogeneous. And that's because the physics of friction and the fault is something that can spontaneously create stress concentrations, perhaps even independently of heterogeneous properties, so it could be a result of the dynamics itself. And so also I don't understand why there was no correlation between plate rate and magnitude. If of all things plate rate should control the recurrence time of large events, but not their magnitude. Plate rate and a constant slip or something would give you different magnitudes, but earthquakes don't produce uniform slip. So I don't even see how this makes sense in the first place.
I'm not. I mean,
I think that it goes back to the ideas of Kanamori and Yada, which preceded Ralph and Kanamori. And I was a very distant witness to their gestation, because Seiya Yada was visiting Caltech when I was a graduate student there many years ago. But they put plate rates in their model, and actually what we tried later on, Seth and myself, in this difflepose business, was to get the rates away and say, well, maybe there's something about plate age, but let's get rid of the rates. So I could agree with you as to, but it doesn't work, even that doesn't work. Now, as for your comment that you have heterogeneity everywhere, and that this argument that Ralph and Kanamori doesn't work, it doesn't necessarily mean that there is a sort of homogeneous universal model independent of all these parameters. If I understand what you're saying is that whether the earthquake grows to big size or stays small, something may have to do with some kind of local heterogeneity, so be it. Then I could reverse the question: what is the nature of that local heterogeneity? You know, and then you are perhaps universal and homogeneous in that you. In that all subduction zones are eventually controlled by these heterogeneities. So one could get the argument that all subduction zones are created equal because they're subject to these local heterogeneities that we don't understand. So it becomes a matter of semantics at the time. But yes, if it's controlled by local heterogeneity, we still have the question mark: what is this heterogeneity?
And I agree with Silvano because basically the elevation of the earthquake can be physically different if we are in the upper part of the subduction zone or in the bottom part of the subduction zone, because it changed the presence of the water, it's changed a lot of, there is a lot of elements that can be totally different. And this is not totally local heterogeneity, this is more kind of general law that can be localized. And this can create a difference in, for example, in the magnitude generation on the rupture itself, linked to the physics of the problem. So heterogeneities can be important not in a really small scale, but in a medium scale. Something like a patch that is more linked to the initial subduction zone or more involved.
Can I say something about the local heterogeneity? And Andy mentioned the local heterogeneity in some zones. They are mainly caused by two processes. One is the slab dehydration fluids, and the second column flow, which cause active volcanoes. And volcano once again cause lateral variation in the thermal structure in the crustal. Okay, which cause the thickness difference seismologically and active faults. These are all heterogeneities, which cause earthquakes and also volcanoes. Tomorrow I will show the tomorrow. We look forward to it.
Let's do this discussion tomorrow.
I still have a question for you, Nito, at some point, which is completely unrelated to this. It's probably like you asked. If I understood your talk well.
Okay.
If I understood your talk well, you have abandoned the idea that there was a kind of precursory motion to earthquake to justify your earlier.
Oh no. This is an orders observation, and it's not really that here is
Okay, you can continue to discuss at dinner. So it's 5 to 10, so at 7 we have dinner. So some people ask for some time for having a break. So we have, so the dinner is between 7 and 8, so you can have some break, and then dinner not too late. And then, well, after dinner we are free. Basically, there is a poster session, which the posters are here in the room next to us, so you're free to go there. We have to have free drinks there, so that people are more encouraged to go. And for the rest, you're free just to go around and visit the place. Thanks. The dinner, the dig is always in the same room. Yeah. I think so. I think it's always there.